Today we're going to be talking about some physics information, and for some of you it will be easy because you've taken physics and you understand a lot of these concepts. For some of you it might not be so easy, so make sure you keep your notes handy. You'll probably be referring to them a lot as you work on this section. So, a little information at the top. According to physics, force equals mass times acceleration. In calculus, acceleration is the second derivative of position. So force is really mass times the second derivative. And the value we often use for the second derivative in normal things happening on the Earth is gravity, 9.8 meters per second squared. Force is measured in newtons in the metric system. A newton is the same thing as a kilogram times a meter per second squared. Our gravitational pull, which I mentioned earlier, is 9.8 meters per second squared. So it says, what is the force necessary to move a 2 kilogram box? Well, force equals mass times acceleration. So force is going to be 2 times 2 kilograms times the 9.8 meters per second squared, which will give us 19.6 kilograms per meter per second squared, which is the same thing as 19.6 newtons. In the English system, force is measured in pounds. So, what is the force necessary to move a 2-pound box? No, this is not a trick question, but it is easy and it may have tricked you. The force is 2 pounds. Now, work is equal to force times distance. In the metric system, work is measured in newton meters, also known as joules, and in the English system, it's measured in foot-pounds. So, example 1 says, how much work is done by lifting a 1.2 kilogram book off the floor to put it on a desk that is 0.7 meters high? Well, this is a metric system, so we need to first find our force. If you remember, force equals mass times acceleration, so our force is going to be 1.2 times 9.8, which will give us 11.76 newtons. And then work is equal to force times distance, so our work is going to be that 11.76 times 0.7, because that's how high we're lifting it, and we are going to get 8.232 joules. Now, it's a little bit easier in the English system because it says how much work is done by lifting a 20-pound weight 6 foot off the ground. Well, we know the English system pounds is force. We already have the force. We know that work equals force times distance, so our work is going to equal that 20 times our 6, which gives us 120 foot-pounds. Now, when we're moving an object from point A to point B, the work that we're doing kind of flex. And we have to add the work that we're doing at each instance, which is why we use an integral. It accumulates the work from point A to point B. So when a particle is located at a distance x from the feet of origin, a force of x squared plus 2x pounds acts on it. How much work is done when moving it from 1 to 3? So, to accumulate the work, we use the integral. So our work is going to be equal to the integral from 1 to 3 of x squared plus 2x dx. We need to anti-derive. And from 1 to 3, it's going to give us 1/3 times 3 cubed plus 3 squared minus 1/3 times 1 cubed minus 1 squared. 27/3 plus 9 minus 1/3 minus 1. And we end up with, you need to see this, I'll show you, 27 thirds plus 27 thirds minus 1/3 minus 3/3. 54 thirds minus 4 thirds will give us 50 thirds. And if you notice, we were measuring in pounds and feet, so work is measured in foot-pounds. Hooke's law, this next one has to do with springs. The force required to maintain a spring stretched x units beyond its natural length is proportional to x. So, equilibrium is when the spring is not stretched or compressed, and then you stretch it. So our formula is force equals the spring constant times x. Let's talk about what that means in this next example. So the force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 to a length of 15. How much work is done in stretching the spring from 15 to 18? Well, good news is we need to consider the length x, and if it was stretched from 10 to 15, that is going to be 0.05 meters. We got to make sure that when you do your spring constants that you always use meters. So if that equals 40, we're going to find that our spring constant, when we solve for k, is 800. Which means for this particular string, f of x equals 800x is the formula that we need to use. Now, we're stretching this spring from 15 to 18. And work would be accumulated that entire time. So we know that to get the work, we need the integral of this force. And it's going to be stretched from 0.05, because 15 is 5 centimeters, 0.05 meters longer than its natural length of 10, to 0.08, because 18 is 8 centimeters, or 0.08 meters longer than its natural length of 10. I went ahead and solved this in my calculator, and when you work this out, you should get 1.56, this time joules, because we are in meters. So we're in the metric system. Try this next spring one on your own, and we will talk about it tomorrow in class, so make sure you come with an answer. And finally, what about lifting something up off a building? So it says a 200-pound cable is 100 feet long and hangs over the side of a building. How much work is required to lift the cable to the top of the building? First of all, we got to come up with a rate. So it's 200 pounds for 100 feet. That makes it 2 pounds per 1 foot. Which means our force is going to be 2x, because it's 2 pounds per foot. Now, we're lifting it, and that work is accumulating, and we're lifting from the whole row. So from lifting 0 to lifting 100 is the integral of our force. So, solve that in your calculator, we end up with 10,000 foot-pounds. And it's foot-pounds because we are in the English system. Now, let's talk for a second. This entire length, let's pretend this is 100 feet long. Occasionally, you will have a question that wants you to lift the first 50 feet of a 100-foot cable. So what you need to remember is that this end is the 0, and this end is the 100, because when you first lift, that cable or rope weighs 200. So if they would ask you to lift the first 50 feet of a 100-pound cable, of a 100-foot cable that's hanging over a building, you would want to do the integral from 50 to 100. The bigger numbers, because you are lifting the heavier portion of the rope. So keep that in mind. You'll run into a question or two like that in your homework tomorrow in class. look this over, let me know if you have questions, or we will